All right, so now that we've looked at our power functions, hopefully we can agree that basically a polynomial is just the sum of a whole bunch of different power functions, perhaps with some coefficients or multipliers thrown in there. And I want to remind you of a couple of definitions that you already know regarding polynomial functions. First of all, the degree of the polynomial is just the highest power in the whole polynomial, and the leading coefficient is the coefficient of that highest powered term. Right? This polynomial is written in descending order, starting with the highest power and working our way down. And in general, that's a good habit to get into when you're writing a polynomial function. All right, so as we work through this unit, we're going to end up asking ourselves a lot of the same questions about higher order polynomials as we asked about the quadratic or second degree polynomials. We might want to look at some different ways to write the analytic form. Remember, we had expanded form and factored form and vertex form, right? We had different ones for the quadratics. We're going to look at different forms for these higher order ones as well. We talked about how to find the zeros, which really comes down to solving the equations. Again, remember with quadratics we had a few ways, like factoring and completing the square and what else? Quadratic formula, square root method, stuff like that. We'll look at methods for these higher order polynomials. We'll want to look at the graphs of higher order polynomials. We'll be building on the graphs of power functions that we've already looked at. We'll want to look at how we use these things in applications, modeling data like we did with the quadratics and the linears. And then can we use them in inequalities as well? So if you kind of look at this outline, hopefully you're going to recognize all the same things that we've already done for linear functions and for quadratic functions. We're now going to do all those same things for these higher order polynomial functions, a new family of functions. All right, so let's see. In this particular section, we're going to be concentrating specifically on the different forms of a higher order polynomial function. And in this case, we're going to be looking at two forms, factored forms and expanded forms. Just like we saw with the quadratics, every polynomial function can be written in an expanded form. Some, but not all, also have a factored form. And when possible, we'd like to be able to go back and forth. So that's what we'll concentrate on in this particular section. We'll start by looking at being given a factored form. How can we get an expanded form? Right? Generally speaking, this is just a matter of multiplying out our polynomial. But in order to multiply out polynomials that have higher powers, it's probably a good idea if we just kind of review the multiplication rules for handling exponents. First of all, notice this is really just two power functions that I'm multiplying together. When I multiply, I actually add the exponents. If you think about that, hopefully it makes sense. For example, if I just take a simple little example like x squared, oops, I'm going to put that in there. Let me start that over so it's more readable. If I have x squared times x to the fourth, x squared really means x times x. X to the fourth really means x times x times x times x. And when you multiply these all together, you now have 6 factors of x. So x to the 6th power. And notice all we really had to do was add the 2 and the 4 to get the total number of factors of x. So using that rule, what would happen if I take x to the 4th times x to the 6th? I would add the powers and get x to the 10th. T to the 3rd times t to the 5th. I would add the powers and get t to the 8th. Negative 4x times 2x to the 8th. I'm multiplying these together, so I really do multiply the coefficients. negative 8. And I'm going to add the powers. Just a reminder, this x here is really a first power, even though it's not written on there. So I'd add the 1 plus the 8 and get x to the 9th. So to multiply power functions, we add the exponents. All right, what if I want to raise a power function to another power? Like x to the a power raised to the b power. In this case, we actually multiply the exponents. And again, if you kind of want to see why that makes sense, what if I wanted to take x to the 4th raised to the 3rd power? That really means to multiply x to the 4th times x to the 4th times x to the 4th. And we already know that when we multiply, we add powers. So 4 plus 4 plus 4 would give me x to the 12th. And I can see that the shortcut to that would have just been multiplying the exponents. So x squared to the 4th power, multiply my exponents, x to the 6th. Excuse me, I wrote it right, I just said it wrong. I multiplied the exponents. 2 times 4 would be x to the 8th power. A to the 5th raised to the 7th power. Again, I multiply the exponents. A to the 35th power. This last one, w cubed to the 3rd power. Multiplying exponents gives me w to the 9th power. All right, last real rule for multiplying. If you have a product raised to a power, it is okay to apply that product, or excuse me, apply that exponent to both factors. Again, if you think about that, hopefully it makes sense. If I had xy to the 2nd power, that really means xy times xy. I have 2 factors of x, so that's x squared. And I have 2 factors of y, so that's y squared. And indeed, that power of 2 ended up applying to both the x and the y. If I try a couple of examples, 2y to the 3rd power, I'd have 2 to the 3rd times y to the 3rd, which I could actually simplify a little bit more. 2 to the 3rd is just 8. So I'm going to get 8y to the 3rd there. On this one, I would have 6 to the 2nd. And with the x, it's already got a power of 7. And then I'm being raised to another power of 2. That's back to this rule again, right? I'm going to multiply the 7 times 2 and get x to the 14th. So I have 36 x to the 14th. One more. This x to the 5th does not have any exponent outside the parentheses. So for right now, I'm just going to leave that the way it is. This 4th power applies to both the 3 and the x squared. So I'd have 3 to the 4th power, then multiplying the exponents, x to the 8th power. I'm going to bring my numerical coefficient to the front. 3 to the 4th power is 81. And x to the 5th times x to the 8th, I'm now back up in this situation, right? So I have to add the exponents. That would be x to the 13th. So just a few simple little examples of handling those multiplication rules. These multiplication rules will crop up as we deal with our polynomials and multiplying them out. This last box talks about what I'm going to kind of jokingly call an unrule. It's an easy mistake to make, but it's one that you really need to work to avoid. We just said that when we have a product raised to a power, the power applies to each factor. Notice that that does not work if I have a sum raised to a power or a difference raised to a power. It is not okay just to say that's x to the n plus y to the n, or x to the n minus y to the n. In fact, if you remember, when you raise something like x plus 4, say, to the second power, how do you actually do that? You actually have to write it out, right? This is a binomial times a binomial. So you have to use either the FOIL process if you learned it that way, or you can think of it as two distributive laws. You'd get x squared plus 4x plus 4x plus 16, or x squared plus 8x plus 16. Notice that if you tried to do this, if you just squared the x, squared the 4, you'd totally miss that middle term. So be really cautious with this one. It's okay when you have a product to just apply the power to each factor, but it's not okay if you have addition or subtraction. You have to write that out and do the whole multiplication process. Just as a quick reminder, let's do one more. If I had 3k minus 4 squared, those are not multiplied together. I can't use this rule. I would have to write it out. And so I'd get 9k squared minus 12k minus 12k plus 16, or 9k squared minus 24k plus 16. Okay. So not a multiplication rule, but one I mentioned because it's a really easy place to make a mistake. Only use this rule if the stuff inside the parentheses is multiplied. If it's added or subtracted, write it out. Okay. So again, best advice with exponents, when in doubt, write it out. If you're uncertain, but you write the multiplication out, like in all these cases, like we did in the center column, it will help keep you from making mistakes. All right, so with those rules in mind, let's take a look at going from factored form to expanded form. You'll notice that I've given you a factored form in each of these, and our goal is going to be to make that into an expanded form, to multiply it out. After we've done that, we'll write down the degree and leading coefficient just for a little practice with the vocabulary. All right, so this time I have 3 factors multiplied together. What I typically will do is just kind of keep one of them aside. I'm just going to keep the x minus 6 the way it is for now, and start by multiplying the other 2. So I'm going to keep the x minus 6 the way it is for now. And then I'm just using brackets to emphasize this is where I'm going to do this multiplication. So x squared plus 2x plus 4x plus 8 which I can write as x squared plus 6x plus 8. All right, now that I've got that done, now I'm going to multiply the x minus 6 into what's left. And you're just going to do this in 2 pieces. I'm going to start by taking the x and distributing that all the way through. So x times x squared, remembering that this is really x to the first. We're going to use that rule about adding the powers. X to the third plus 6x to the second plus 8x. And then I'm going to take this negative 6 and I'm going to distribute that all the way through. So negative 6x squared, negative 36x, and negative 48. All that's left to do is combine any like terms, and I'm going to take care of my descending order as I do this. So the x cubed is the only x cubed term. In this particular one, the x squareds just happen to add up to 0, so I will have a 0 x squareds. I won't even have to write that. The x to the first, I would have a negative 28x. And then the constant term, negative 48. So this would be the expanded form of my function. I'll multiply it out. It is, notice, degree 3, and the leading coefficient is just 1. All right, let's try a couple more. B of A is defined as this product. And again, there's 3 multipliers. So what I'm going to do is just keep the first one the way it is for now, a to the 4th. And then I'm going to multiply out those 2 binomials. A squared times 3a to the first would be 3a to the 3rd. I'm adding powers. Minus a squared plus 15a minus 5. This time I can't combine anything, so I can just go ahead and start distributing this a to the 4th all the way through here. Again, multiplying means adding exponents. So 3a to the 7th, subtract a to the 6th, plus 15a to the 5th, minus 5a to the 4th. And that is now completely multiplied out, so that is the expanded form. My expanded form here had degree 7, and the leading coefficient is the 3. All right, we got a couple more. G of n, 2n squared minus 3 to the 3rd power. First of all, I know because it's subtraction, it's not as simple as just putting the 3rd power on both of those. Instead, I'm going to start by writing this out. What does this really mean? It means 2n squared minus 3 times 2n squared minus 3 times 2n squared minus 3. This is actually very similar now to the first problem we did with 3 binomials. So if you want to practice a little bit, I might recommend pausing the video here and giving this a shot. And I'm going to go ahead and do it now. So hopefully if you've already paused it, you already have an answer that you can check. All right, I'm going to keep the first factor the way it is, and I'm going to concentrate on multiplying out the last 2. I would get 4n to the 4th minus 6n squared minus 6n squared plus 9. And I can combine these 2 middle terms. So that's actually 4n to the 4th minus 12n squared plus 9. All right, I now have to distribute each term from this binomial through that whole trinomial. So I'm going to start with the 2n squared. I would get 8n to the 6th negative 24n to the 4th and then a plus 18n squared. Next, I'm going to distribute the negative 3. I'll get negative 12n to the 4th, positive 36n squared, and negative 27. All right, I probably should have written a little smaller, but we're going to squeeze this in down here. 8n to the 6th, that's going to be my highest degree term. Combining the n to the 4th terms, I've got negative 36n to the 4th. And combining the n squared terms looks like a positive 54 n squared. And then finally the minus 27. So there is the expanded form for g of n. We ended up with a 6th degree and a leading coefficient of 8. All right, I've got one more for us here. P of x is 3x squared squared times 4x plus 1 squared. Now this one's really here to remind you when you can and when you can't. Just take that power and bring it out into the parentheses. This is a product, so it's perfectly okay here for me to say that would be 3 squared times x to the 4th, right? Because those are multiplied together, I can simply apply that second power to both the first and second factors. This is not a product. This is a sum inside this parentheses. So this I'm going to have to write out as a binomial times a binomial. And I'll have to do FOIL or distributive laws or whatever you want to call it. All right, so right now, let's see, 3 squared, that would be 9x to the 4th. I'm going to leave that, and I'm going to concentrate on multiplying those two together. 16x squared. I'll show you a little something here. When you have, if you're thinking FOIL, you'd think of it, oops, I need something that writes better than that. You'd think of it as the outers and the inners. If you can see that, oftentimes those combine. And if they do, and you can kind of see it mentally, it's nice if you could take a little shortcut here. Saves yourself writing out a step. Just think plus 4x is plus 8x. Right? If that messes you up, don't do it. Write it all out. But if you're to the point that you feel like, hey, I could probably do the outers and inners and combine them in the same step, it will save you a little writing. All right, and then the last would be a plus 1. All right, now I can take this 9x to the 4th and distribute it into my brackets. So 9 times 16, is that 144? I think it is, but let me double check on that. Yeah, 144. Adding the exponents would give me x to the 6th plus 72, and that'll be x to the 5th plus 9x to the 4th. So this one's got a degree of 6 and a leading coefficient of 144. All right, so that's expanding. And before we move on to factoring, which we'll do in just a couple minutes here, I wanted to mention something to you about these degrees. By the time it was all multiplied out, it was pretty obvious what the degree of each of these was. But could you have predicted the degree even before you multiplied out? Let's think about that for a minute. In this first one, I was multiplying 3 binomials, x times x times x. That's actually where that x cubed came from. And I could have predicted that the degree was going to end up being 3, even before I multiplied it all out. What about this next one? I had a to the 4th, I had a squared, and I had a to the 1st, all being multiplied together. When you add those exponents, 4 plus 2 plus 1, I could have predicted that the degree was going to be 7. Again, even before I did all the work of multiplying it out. Here, I have n squared, but it's being raised to the 3rd power. A power raised to another power, we multiply exponents. 2 times 3 would have given me a 6th power. And this last one's probably the most complicated of all, but I think we can do it. We have x squared squared, and then we have another x being squared here. So if I really think hard about this one, that'll give me an x to the 4th. This will give me an x squared, and I end up with a degree of 6. It's kind of an interesting exercise to go through right now, but we're going to find out a little bit later in this unit when we start graphing these higher order polynomials that being able to quickly predict the degree, even from the factored form, actually will help us with graphing. So it's a good exercise to kind of lead yourself through as you go through this. All right, so we've now gone from factored form to expanded form. What about the other way around? What if I want to go from expanded form to factored form? Okay. First of all, good news. The factoring techniques that you've already used on quadratics will often help us with the factoring of higher order polynomials. So watch for a lot of the same kinds of things that we've been doing. And in particular, don't forget the very first step in factoring. Check for GCF before you do anything else. That hasn't changed. Right? That said, here are some important factoring techniques when we're dealing with the higher order polynomials, degrees larger than 2. First of all, the grouping method. Okay. This is a good choice to try if the polynomial that you're trying to factor has 4 terms. Okay. So we got 4 terms, we're going to try grouping. We've actually seen this method before kind of as a sub-method in something we've already done. I think you're going to recognize it. So I'd like to factor it, or if I can't factor it, I'll say that it's prime. And looking at my first function, h of x, I'm going to notice that there is no GCF that works for all 4 terms. So instead, I'm going to use a grouping method. Grouping, I just create 2 groups, or 2 pairs of terms. And now instead of finding a GCF for the whole thing, I'm only looking for a GCF within each pair. So in the first pair, x squared is my GCF. And when I factor that out, I get x to the 1st plus 5. In the second pair, I'm going to notice that there's a minus sign between the groups, so I'm going to factor out a negative. And then these are both divisible by 4. That's going to leave me x here. And negative 20 divided by negative 4 makes that a positive 5. Just like we saw in the past, in order for grouping to work, those must match. You have to have the same binomials from each factoring process. Otherwise, the grouping didn't work. And you have to kind of go back and say, is there anything else I could have done? Or maybe it's prime. But this time it did work. So I'm going to factor out the common binomial, x plus 5. When I factor it out of this first term, I have the x squared left. And when I factor it out of the second term, I have the negative 4 left. So there's my grouping method completed. But I actually don't think I'm done with this problem. Do you recognize that as something you learned how to factor back with the quadratics? That's a difference of squares, right? If I wanted to, I could think of it as x squared minus 2 squared. So I'm going to continue to factor. I'm done with the x plus 5. I'm going to keep that the way it is, but then I'm going to factor that difference of squares as x plus the 2 and then x minus the 2. That's our difference of squares pattern, or another way of thinking of it is x squared is x times x. Negative 4 is positive 2 times negative 2. And remember, this is the one where the inners and the outers cancel each other out. There's a positive 2x and a negative 2x, which is why we didn't have a middle term here. All right, now I think I'm finally done getting my factored form for h of x. Done everything I can. Let's try another one. F of w here. This time I think I do see a GCF will work for all 4 terms. So we're going to deal with that first. 3 goes into all of the coefficients. And the smallest power of w is just w to the first, so I can factor that out. When I do that, I'm going to get 2w cubed plus w squared plus 8w plus 4. 3w is my first factor. I'm kind of done with it, so I'm just going to keep it out here the way it is. And personally, I like to use brackets when I'm going to kind of do some more work with another part of the problem, which I'm going to do right now. 4 terms, so I'm going to go ahead and do grouping inside of here. And I could factor out a w squared in the first group, which gives me 2w the first plus 1. Remember, w squared divided by w squared. It's 1, not 0, right? You have to put that 1 there. Plus sign in between my groups. And in my second group, I could factor out 4. 8w divided by 4 is 2w. 4 divided by 4 gives me the plus 1. Double checking to make sure the grouping actually worked. And it did, right? Those match. So going to the next step, I keep that 3w, bring it along, right? Otherwise you're going to forget it at the end. And then I'm going to say, I can now factor out the common binomial, 2w plus 1, which leaves me the w squared from here and the plus 4 from there. As long as one of my factors still has a square in it, I always ask myself if I could go any further. But in this case, the answer is no. Remember that the difference of squares is factorable, but the sum of squares is not. Just reviewing a little bit from the last unit. So this is actually my final form. This is the factored form of f of w. All right, so that's what you do if you have 4 terms. Try that grouping method. What if we don't have 4 terms? What if we have 3 terms? When we have 3 terms, what we usually want to do is check and see if we have something called quadratic form. If you remember a general quadratic, let me just remind you. Of the form ax squared plus bx plus c. That middle term, that x is really a first power, although we don't often write it. But it's true, right? It is. What I want you to notice specifically here is in those first 2 terms, there's a specific relationship between the powers on the x's. The power here is exactly double the power there. Any function where that relationship exists, the first power is double the second power, we say is in quadratic form. So whatever the power is here, and I'm just going to call it n in general, if the first power is exactly double that, 2n, then my trinomial is in quadratic form. Right? If you've checked and your trinomial is in quadratic form, then we can use the same sum and product techniques that we practiced in the last unit. Okay? So if you have quadratic form, we're going to end up with sum and product. All right, so let's give this a try. First of all, let's just verify that we really do have quadratic form. When I look at my exponents, 3 and 6, that looks really good, right? The first exponent of 6 is exactly double the second one. So quadratic form, yes. Don't try to use this technique if it's not quadratic form, but this one is. So I'm going to look at this and say, okay, I can start, because I have a leading coefficient of 1, I already know that this v to the 6th is just 1v cubed times 1v cubed, right? Notice how I broke the v to the 6th into two equal factors, v cubed times v cubed. To figure out the values here and here, I'm looking for a sum of 11 and a product of 18. So 2 and 9. So v cubed plus 2, v cubed plus 9. And there's my factored form. All right, what about b? Trinomial again. Is it quadratic form? Well, yeah, the first power is exactly double the second one. So yes, we are looking at quadratic form. Now this one, with the leading coefficient that's not 1, we have to go through a little bit more work to get the factored form. Right, this is the one where I say the sum is still negative 35. But I have to multiply those, and my product is negative 36. So I'm thinking 1 and 36 here, with the negative on the 36. That way it'll add up to negative 35. So I'm going to keep the 4x to the 4 the way it is for right now, and then I have to break apart the middle term. I'm going to write that as plus 1x squared, and then minus 36x squared. Make sure you're paying attention to the power here. If this is x squared, when I break it apart, both of those terms have to be x squared terms. So they could be combined back to the original if I needed to. All right, and then I have a minus 9. All right, I now do have 4 terms. So at this point, I can use the grouping method. My first group, I'm going to factor out x squared, which makes that 4x squared plus 1. Minus sign between the groups, so I'm going to factor out a negative, and 9 goes into both of those. So let's see, negative 36 divided by negative 9, positive 4x squared, negative 9 divided by negative 9, positive 1. Looks like our grouping method worked. We do have the same binomial in the parentheses. So I'm going to factor out that 4x squared plus 1, which leaves me this x squared, and in that one it leaves me the minus 9. All right, this time I don't think I'm done. This is a sum of squares, so I am done here. But notice the difference of squares that's happening there. I can think of that as x squared minus 3 squared. So I'm going to leave the 4x squared plus 1 the way it is. But I'm going to factor this as x plus 3 times x minus 3. So be aware when you're factoring these higher order polynomials, not every time, but sometimes there's that extra step. Just watch for it. Always look at your answer and analyze it. You know, have I found everything, or do I potentially have more to factor? Now I think I'm actually done because, again, sum of squares I can't factor. All right, got one more trinomial. And this time, first of all, if I even just quickly at a glance thought about quadratic form, I'd notice right away it doesn't work, right? 7 doubled is not 12. But as I take a little bit longer glance at this, I think I probably need to be factoring out a GCF before I even think about anything else. So let's do that. 4 goes into all of the coefficients, and I could factor out the t squared. So that is going to leave me t to the 10th, right? 2 plus 10 gets the 12. Minus 9 t to the 5th. Plus 14, just 14. All right, now look inside the parentheses. Are we at quadratic form at this point? And yes, we are. The first power is exactly double the second one. So I'm going to keep my 4t squared. I'm done with that part, but it has to come along for the ride, otherwise I'll forget it when I write the final answer. And this one I'm thinking, okay, I do have a leading coefficient of 1 inside my parentheses, so I could split this up right away as 1t to the 5th times 1t to the 5th. Then I'd be looking for a sum of negative 9 and a product of 14. So I'm thinking negative 2 and negative 7 would do that. T to the 5th minus 2, t to the 5th minus 7. And these aren't difference of squares, certainly, but the 5th power is in there, so I know I'm done. All right, so we got 4 terms we're going to use grouping. 3 terms we're going to look for quadratic forms, so we can use sum and product. And finally, what do we do when we have binomials? Okay. So this last piece is about factoring higher order binomials. There are actually 3 possibilities here, one of which you're already familiar with, the difference of squares, right? We've been using this one already today, and we know how to factor it. U squared minus v squared is u plus v times u minus v. Now I want to keep in mind that this is still going to work even if I have higher powers. So, for example, what if I had x to the 8th minus, let's see, let's just go with, sorry, should have made this one a bit in advance. Let's just go with 25. I need to recognize that that x to the 8th is a perfect square. It's x to the 4th squared minus 5 squared. So even though you might not look at that and say, hey, that's a perfect square, it really is. In fact, any even power can be written as something squared, right? And then I could use my difference of squares pattern to do x to the fourth plus 5 times x to the fourth minus 5. So even though that formula is written for a difference of perfect squares, we might start out with a higher power that we can reconsider as a square. All right, the next two are new. The difference of cubes and the sum of cubes. These we haven't seen before, at least not in this class. These formulas are a little bit more complex, let's say, right? There's a lot more involved, and they don't come up nearly as often as the difference of squares. So I am going to tell you that although I expect you to know this little formula for factoring a difference of squares, these two are formulas that I do provide to you, like on the midterm and final, when you have to do them without looking. So you'll have the formulas, you just need to know how to use them. Right? These, if you at your leisure some point would like to try, I would encourage you to multiply this out using our expanding technique and just verify to yourself that they actually do give you u cubed minus v cubed and u cubed plus v cubed. But to keep this video a reasonable length, I'm just going to go ahead and accept those for right now and move ahead to the factoring process. So on the top of the next page, we have a summary of all of our binomial factoring formulas. The difference of squares, the difference of cubes, and the sum of cubes. So let's try this out. In my first example, I have 8x to the third plus 125. The only possibility here would be this one, right? It's the only one that's a sum. And so I'm going to ask myself, are these both perfect cubes? Could I write them as something cubed plus something cubed? And the answer is I think I can. 8 is 2 cubed. And then I have the x here, so 2x to the third power would indeed be 8x cubed. And 125, you can just try it on your calculator, but you may recognize that as 5 cubed. So I truly do have the sum of cubes. In my formula over here, I'm just going to make a note to myself. U is going to get replaced with 2x, and this v is going to get replaced with 5. Okay. So now all I'm going to do is use my formula and make those replacements. So I start with u plus v, 2x plus 5. In the next parentheses, excuse me, I have u squared. So that's really the whole 2x being squared. Minus u times v, so minus 2x times 5, plus v squared, plus 5 squared. I'm going to simplify a little bit inside that second set of parentheses. So I have 2x plus 5, 2x squared, 2 squared would be 4, and then I have the x squared, minus 10x, plus 25. That is now completely factored, and I'm going to give you a little shortcut. Yes, I know this is a trinomial, and maybe we should be thinking about sum and product, but I'm going to tell you that if you have correctly used the difference or sum of cubes formula, the trinomials that you get here will never be factorable. So guaranteed you won't be able to factor this any further, and we can just stop. That trinomial will be prime every time. So take that as a shortcut, and it'll save you some time of wondering or checking. All right, in B, This one, as I look at that, right now it doesn't look like squares or cubes, but then I'm going to kind of notice, wait a minute, there's a GCF here, right? And we should always factor out a GCF as our first step if we have one. So I'm going to factor out a 2a. It's going to make that a to the 8th minus 49. All right, with the subtraction here, I do have both options of squares and cubes, but the 8th power is going to be for a square, and 49 is definitely a square, not a cube. So I'm thinking this time difference of squares. I can think of this as a to the 4th squared minus 7 squared. And if you want to, you can write this out as u becomes a to the 4th and v becomes 7. Although you've done these so many times, you probably don't even need to do that. And then I just have u plus v, so a to the 4th plus 7, and u minus v, a to the 4th minus 7. And like I said, because we've used difference of squares before, and it comes up much more often than the cubes, that is the one formula here that I expect you to have memorized. Again, you've probably already been using it without looking at formulas, so shouldn't be a big deal.